So we've got a question here about cricket now, projectiles and vectors all together. So here we've got the cricketer striking a ball. And what I've done here is to draw a little diagram with the cricketer standing roughly here and striking the ball at 22i plus 3j, the I direction and the j direction are those directions there, and the trajectory of the ball is such that it's going to be caught at this point here, which is below the point at which the ball is struck, and I'm taking that as the origin. So for part A, we're trying to find the speed of the ball after 2 seconds. So this is a particle which is moving freely under gravity, so we can use suvat. So the displacement we're not interested in for part A. We've got the initial velocity, again taking the origin as the point at which the ball is struck. The final velocity is v, because that's what we're trying to find, the speed of the ball after 2 seconds. The acceleration is minus 9.8, and I'm taking that and that as the positive direction. So the acceleration due to gravity has just got a component in the j direction. It hasn't got any I component at all. So the formula, which doesn't have the s in it, is v equals u plus at. So there's our numbers going into the formula, and that's our velocity after 2 seconds. So the speed of the ball is the magnitude of that velocity, and using Pythagoras we get a speed of 27.6 meters per second. So now what we want is an expression for the position of the ball relative to the point of impact with the bat. So this is the origin, the point of impact with the bat. So for part B, we're going to use suvat again, and we're trying to find the position of the ball, which is s. We've got the initial velocity, the acceleration. We're not interested in the final velocity this time, and we're going to take the time as capital T. This is a general position of the ball at time t. So the formula we're using is the one that doesn't have v in it, s equals ut plus half at squared. And when we put our u, a and t into there, we get that expression. And all I've done there is to group the I and the j components separately. So for part C, we're trying to find the horizontal distance, and we're told that the ball is caught at a height of 0.5. So the ball is caught here. So the position vector of the ball, when it's caught, it will have an an I component of x, I'm calling it, but the j component is going to be a negative component. It's going to be 1.1 meters lower than it was when it was struck. So that means that the ball is caught relative to the point of impact at the position vector xi minus 1.1j. So that means that this is x and this is minus 1.1. So we're looking to, we've got these two equations. Using the second of these, using this equation, we can solve that for t. And that gives us a t of 0.87 seconds. And when we put that time into there, we'll find the value of x, which is 19.1 meters. So caught out. Oh, there we are.